Out of the hundreds of billions of stars that populate our Milky Way galaxy, only around 30 are so extraordinary that they defy almost everything we understand about stellar physics. These stars are not just rare, they are cosmic anomalies, each one a blazing testament to the extremes of the universe. Unlike ordinary stars that burn steadily for billions of years, these celestial objects harbor forces so immense that they can distort matter itself and unleash energy that could outshine entire galaxies for a fleeting moment. Their magnetic power is beyond anything humans can practically comprehend, and their existence challenges our perception of what stars can be. To put it simply, they are the rarest, most extreme monsters of the cosmos, and yet they are real. These extraordinarily rare cosmic objects, with their magnetic fields and violent outbursts, belong to a category of stars that is unlike anything else in the universe: magnetars. At their core, a magnetar is a type of neutron star, a remnant left behind after a massive star ends its life in a supernova explosion. Neutron stars themselves are already exotic. They pack a mass greater than that of our Sun into a sphere only about 20 kilometers across, meaning a single teaspoon of neutron star material would weigh about 1 billion tons on Earth. Yet magnetars take this strangeness to a level almost incomprehensible. What sets them apart from typical neutron stars is the intensity of their magnetic fields, which are billions to trillions of times stronger than any magnetic field we can produce or observe elsewhere. To grasp the scale, Earth's magnetic field is about 0.5 Gauss. The strongest magnetic fields humans can create in labs are tens of millions of Gauss, but magnetars can exceed 10 to the 15th Gauss, a quadrillion times stronger than our planet's field. These magnetic fields are so powerful that they can twist space-time, distort atoms, and influence fundamental forces in ways that physicists are only beginning to understand. Magnetars are not only magnetic powerhouses, but also reservoirs of energy stored in the very fabric of their structure. Their magnetic fields are so immense that they affect the star itself. The surface of a magnetar is under such intense magnetic pressure that it can crack and shift, causing starquakes, phenomena that release a sudden burst of X-rays and gamma rays into the universe. These bursts are unimaginably energetic. Even a relatively small flare from a magnetar can release as much energy as our Sun emits in tens of thousands of years. It is this combination of extreme density, intense magnetism, and unstable crust that makes magnetars so uniquely terrifying and fascinating to astronomers. They exist in a precarious balance, where the slightest change in their interior or magnetic configuration can trigger violent eruptions visible across vast interstellar distances. Another remarkable aspect of magnetars is their spin. While neutron stars in general are fast-spinning, magnetars rotate relatively slowly in comparison, typically completing one rotation every 2 to 12 seconds. Despite this slow spin, their magnetic fields are far more intense than even the fastest spinning pulsars. Scientists believe that the slow rotation is not a weakness, but a consequence of how magnetars form. The mechanisms that amplify their magnetic field to these phenomenal strengths also sap angular momentum, leaving them spinning slower than other neutron stars. The interplay between their rotation and magnetic field creates dynamic interactions in their magnetosphere, generating high-energy radiation and possibly triggering the sporadic bursts that make them observable from Earth. Magnetars are often identified through the dramatic signals they emit, rather than their visible light. Unlike ordinary stars that shine steadily in optical wavelengths, magnetars are faint in visible light, but can be extraordinarily bright in X-ray and gamma-ray bands. The energy stored in their magnetic fields eventually leaks outward in violent outbursts or steady emission of high-energy radiation. These emissions, sometimes intermittent and sometimes sustained, are how astronomers detect and study them across the galaxy. Because of this reliance on high-energy observation, many magnetars may go unnoticed until they flare dramatically, suggesting that while only about 30 have been confirmed, there could be more hiding in the cosmic shadows, waiting for a flare to reveal their presence. Understanding what a magnetar truly is also involves appreciating the paradox of its existence. It is both a product of extreme violence and a source of it. Born from the death throes of a massive star, a magnetar emerges from a supernova, itself a spectacular explosion that disperses heavy elements across the galaxy. Yet, as a newborn neutron star, it carries with it a magnetic field that can outstrip anything the original star could generate. Its field is thought to be a result of a dynamo effect during the first few seconds of its life, when the proto-neutron star is still hot, fluid, and spinning rapidly. Under these conditions, small perturbations in the star's motion and charge distribution can become amplified exponentially, creating the extraordinarily strong magnetic fields we observe. It is this combination of birth in violent death and subsequent magnetic intensity that makes magnetars simultaneously fascinating laboratories for physics and terrifying engines of cosmic energy. To fully grasp the extraordinary nature of magnetars, one must consider their rarity in the context of the broader stellar population. Our galaxy alone is home to hundreds of billions of stars, yet only a handful of these exhibit the extreme characteristics that define a magnetar. The vast majority of stars are ordinary, steady-burning objects. Red dwarfs, which are the most common type of star, make up the bulk of stellar populations, with their low mass, low temperature, and lifespans stretching tens to hundreds of billions of years. These stars, while fascinating in their longevity and stability, pale in comparison to the energetic extremes of magnetars. For every single magnetar, there are billions of red dwarfs quietly shining, emphasizing just how extraordinarily rare magnetars are. Moving up the scale in mass and temperature, we encounter white dwarfs. These are the remnants of stars like our Sun, dense and slowly cooling over billions of years, slowly fading into obscurity. There are millions of white dwarfs in the Milky Way, each a fossil of a star that has exhausted its nuclear fuel. Though dense and scientifically intriguing, white dwarfs do not exhibit the violent magnetic behavior characteristic of magnetars. They are stable, mostly inert objects compared to the volatile energy bursts that can erupt from a single magnetar. If red dwarfs are the calm, ubiquitous background of our galaxy, and white dwarfs are the retired, dim veterans, magnetars are the few, explosive celebrities whose presence dominates a region of space, albeit fleetingly. Even pulsars, which are themselves exotic neutron stars emitting regular beams of radiation, vastly outnumber magnetars. Thousands of pulsars have been catalogued in our galaxy, and while they are remarkable for their precision and their strong magnetic fields, they are generally far less extreme than magnetars. A typical pulsar may have a magnetic field in the range of 1 trillion Gauss, which is enormous by human standards, but still dwarfed by the quadrillion Gauss fields of a magnetar. Pulsars are often discovered because of their periodic radio signals, which sweep across Earth like cosmic lighthouses, whereas magnetars reveal themselves more sporadically, sometimes only through sudden X-ray or gamma-ray flares. This sporadic visibility adds to their mystique and makes them harder to detect, contributing further to their perceived rarity. To put this into perspective, consider the numbers. If the Milky Way contains roughly 100 billion stars, perhaps tens of millions are neutron stars left behind by massive stellar deaths. Thousands are observed as pulsars, and only around 30 are confirmed as magnetars. Statistically, that means for every magnetar, there are billions of ordinary stars and hundreds of thousands of other neutron stars. They are cosmic needles in a vast galactic haystack, almost impossibly rare. This extreme scarcity is part of what makes studying them so valuable. Each observation of a magnetar provides a unique opportunity to understand physics at limits that cannot be replicated anywhere else, from magnetic forces and dense matter behavior to the mechanisms behind high-energy cosmic events. Their rarity is not just a matter of numbers, but also of the precise conditions required for their formation. Unlike ordinary stars, whose births and deaths follow well-understood patterns, only a tiny fraction of massive stars have the right combination of mass, spin, and internal dynamics to emerge as a magnetar. Many massive stars explode in supernovae and leave behind regular neutron stars or black holes. Some collapse with the right parameters, but fail to achieve the magnetic amplification necessary to become a true magnetar. This combination of extreme rarity in both occurrence and observable phenomena cements their status as one of the universe's most exclusive and mysterious classes of celestial objects. The story of a magnetar truly begins with the death of a massive star, a violent and transformative process that is among the most extreme events in the cosmos. Stars that eventually become magnetars are not your average stars. They must possess substantial mass, typically between 20 to 40 times the mass of our Sun. Throughout their lifetimes, these stars burn nuclear fuel at tremendous rates, fusing hydrogen into helium, helium into carbon, and eventually forming layers of heavier and heavier elements in their cores. This intense fusion leads to an equilibrium where the outward pressure from nuclear reactions counterbalances the inward pull of gravity. Yet, as with all massive stars, there comes a point when the fuel runs out, the core can no longer sustain fusion, and gravity takes over. The result is a catastrophic implosion, an event we know as a supernova. Unlike ordinary neutron stars that also form from supernovae, the birth of a magnetar requires highly specific conditions during this collapse. When the star's core implodes, it compresses matter to densities higher than that of an atomic nucleus, producing a neutron star in a matter of seconds. But for a magnetar, the conditions must align in a very particular way. The progenitor star needs to have an extremely rapid rotation in its final moments. This spin, combined with turbulence in the collapsing core, drives a dynamo effect, a process in which motion within a conductive fluid generates and amplifies magnetic fields. The result is a magnetic field amplified to mind-boggling levels, reaching quadrillions of Gauss, far beyond anything seen in regular neutron stars. These are not incremental increases, they are exponential, the result of chaotic, rapidly moving charged particles inside the proto-neutron star amplifying small pre-existing magnetic fields by many orders of magnitude within the first few seconds of the star's life. The exact mechanisms behind this magnetic amplification are still an area of active research, but the prevailing theory involves what is sometimes called the alpha-omega dynamo. In this scenario, the differential rotation of the collapsing core stretches magnetic field lines, while convection and turbulence twist and tangle them, effectively converting kinetic energy from the star's collapse into magnetic energy. This is why magnetars are so rare. Only a very narrow range of progenitor stars possess the right combination of mass, rotation speed, and internal dynamics to sustain this dynamo effect during collapse. If the spin is too slow or the internal turbulence insufficient, the star may still form a neutron star, but it will not reach the magnetic extremes required to be classified as a magnetar. If the mass is too high, the collapse might form a black hole instead, erasing any chance for a magnetar to exist. Another critical aspect of their birth is the supernova explosion itself. Unlike standard supernovae, that distribute elements relatively evenly into space. The formation of a magnetar may involve asymmetric explosions due to the extreme rotational forces and magnetic stresses. These asymmetries can influence how the outer layers of the star are ejected, potentially affecting the observable properties of the resulting supernova. In some cases, magnetars are associated with highly luminous supernovae, known as superluminous supernovae, which may be powered in part by the rapid rotation and intense magnetic energy of the nascent magnetar pumping energy into the expanding ejector. This connection hints at the profound impact a magnetar can have not just on its immediate surroundings, but also on the chemical enrichment and evolution of galaxies themselves, spreading elements forged in the progenitor star across interstellar space. Interestingly, the birth of a magnetar is also tied to the star's environment before collapse. Observations suggest that magnetars often emerge from progenitors in regions with relatively low metallicity, meaning fewer heavy elements in the star's composition. Low metallicity allows stars to retain more of their mass and rotational momentum over their lifetimes, which is crucial for the conditions that produce the alpha-omega dynamo effect during collapse. Conversely, stars with high metallicity lose significant angular momentum due to stronger stellar winds, reducing the chances of forming a magnetar. This delicate balance between mass, rotation, metallicity, and collapse dynamics underscores why magnetars are extraordinarily rare in our galaxy, and why each one represents an almost unique event in the cosmic timeline. Once born, the newborn magnetar is already a cosmic powerhouse. It emerges from its supernova with rotation periods of mere milliseconds and magnetic fields so extreme they dominate the behavior of the star. In these first moments, it is highly unstable. Its outer crust, forged from ultra-dense nuclear matter, is under immense stress from the magnetic field and rotational forces. The star is alive with seismic activity, and starquakes may occur almost immediately, releasing bursts of radiation and helping to stabilize the magnetic field configuration. These initial bursts, detectable as high-energy X-rays or gamma rays, are among the first signs that a magnetar exists. Even though it may reside tens of thousands of light-years away, its extreme birth ensures that it is never truly silent on the cosmic stage. The birth of a magnetar is only the beginning of a story defined by forces so extreme that they defy ordinary comprehension. Among the defining features of these cosmic anomalies is their magnetic field, a force so intense that it pushes the boundaries of physics as we understand it. To truly grasp the magnitude of a magnetar's magnetic field, one must consider that it can reach a quadrillion times stronger than Earth's. Earth's own magnetic field, which guides compasses and protects us from solar wind, measures roughly 0.5 Gauss. In contrast, a magnetar's magnetic field can soar beyond 10 to the 15th Gauss. Such strength is not merely a matter of scale. It transforms the behavior of matter at a fundamental level. At these field intensities, the usual rules of atomic and molecular interactions begin to warp. Electrons are forced into spiral paths along magnetic field lines, and atoms themselves become elongated, squeezed into needle-like shapes instead of their ordinary spherical forms. Matter as we know it literally cannot exist in the same way on the surface of a magnetar. These magnetic fields are not static either. They are dynamic, constantly interacting with the star's structure and the space around it. The field exerts tremendous stress on the crust, twisting and contorting the ultra-dense material in ways that can lead to starquakes. These quakes are akin to earthquakes, but magnitudes larger, and they release bursts of high-energy radiation detectable across the galaxy. The field is also responsible for confining a highly charged plasma atmosphere just above the star's surface, which can influence the magnetars' emission of X-rays and gamma rays. The magnetosphere of a magnetar, shaped by this intense magnetic pressure, is a region where light and radiation themselves behave unusually, bending and being redirected by the forces in ways impossible around less extreme stars. In some sense, a magnetar is not merely a star. It is a cosmic laboratory where matter, energy, and magnetic fields exist in a regime entirely inaccessible to human-made experiments. The origin of such a colossal magnetic field is rooted in the star's formation and rapid initial rotation. During the first seconds after collapse, the proto-neutron star's rotational energy and turbulent convection amplify the magnetic field exponentially through a dynamo effect. This is not a gradual increase over millions of years, but an almost instantaneous surge that turns a normal neutron star into a magnetar. Scientists theorize that in this state, the field can reach a critical intensity that interacts with the star's internal particles, compressing them, altering their spin, and even affecting the behavior of quantum fields. In essence, the magnetar's magnetic field is not just strong. It is capable of bending the fundamental building blocks of matter in ways that challenge our understanding of physics. These fields also influence the surroundings of the magnetar far beyond its surface. The immense magnetism can accelerate particles to near light speeds, creating streams of charged particles that travel into space. When these particles collide with the interstellar medium, they can generate additional high-energy radiation, making magnetars detectable even from tens of thousands of light-years away. Furthermore, the magnetic field's interaction with space-time itself can lead to exotic phenomena, such as the formation of magnetically dominated bubbles in the surrounding medium. In some ways, a magnetar shapes the space around it as forcefully as it dominates its own surface, acting as both a cosmic engine and a sculptor of its immediate environment. Perhaps the most mind-bending aspect of a magnetar's magnetic field is the sheer impossibility of replicating it anywhere on Earth. The strongest human-made magnetic fields, achieved in laboratory experiments, reach tens of millions of Gauss, a number that sounds large but is utterly insignificant compared to a magnetar's trillion-plus Gauss field. The difference is not merely quantitative, but qualitative. Under a magnetar's magnetic field, atoms are no longer ordinary, electrons are constrained, and even the vacuum of space behaves differently. Electromagnetic forces that are normally negligible in ordinary stars or laboratory experiments dominate every aspect of the star's behavior. It is a regime where theory strains to predict outcomes, where relativistic and quantum effects intertwine, and where our familiar understanding of matter, energy, and physics breaks down entirely. The magnetic field also plays a pivotal role in one of the most dramatic manifestations of a magnetar's power, starquakes and subsequent bursts of radiation. These magnetic stresses literally twist the crust of the star to the breaking point, releasing energy equivalent to what the sun would emit in 100,000 years in just a fraction of a second. The field's intensity determines not only the magnitude of these bursts, but also the frequency and character of the radiation emitted. It is this dynamic interaction between the magnetic field and the star's dense matter that makes each magnetar a unique cosmic phenomenon. No two magnetars are identical. Slight variations in magnetic field structure or internal stresses can produce wildly different behaviors, further complicating efforts to understand them comprehensively. In short, the magnetic field of a magnetar is more than a feature. It is the essence of its identity, the force that defines its existence, behavior, and influence on the cosmos. It is a field so extreme that it challenges our very understanding of physics, warps matter and space-time, and powers some of the most energetic events in the universe. Without this magnetic intensity, a magnetar would be just another neutron star. With it, it becomes one of the rarest and most violent objects in existence, a cosmic powerhouse whose effects ripple across the galaxy in ways that are both observable and theoretically profound. Beneath the staggering magnetic field of a magnetar lies a surface unlike any other in the universe, a crust forged from ultra-dense, iron-like matter that challenges the limits of what we consider solid. While a typical neutron star's crust is already extraordinarily dense, packing more mass than Mount Everest into a teaspoon, a magnetar's crust is under even greater stress due to its immense magnetic field. This field exerts forces so powerful that they distort atomic nuclei themselves, stretching and elongating them along magnetic field lines. The crust is not a smooth, tranquil layer. It is a brittle, shifting landscape where tension builds continuously until it is violently released in the form of starquakes. These starquakes are not minor tremors. They are catastrophic ruptures that can rearrange vast regions of the crust almost instantaneously, sending shockwaves through the star's interior and triggering bursts of electromagnetic radiation detectable across the galaxy. The material in a magnetar's crust is primarily composed of neutrons, protons, and electrons arranged into an incredibly dense lattice, often described as nuclear pasta, because of the strange, layered formations it can take under such extreme conditions. This nuclear pasta is thought to exist in shapes resembling lasagna sheets, spaghetti-like filaments, or gnocchi-like blobs, depending on the pressures and forces at play. Under ordinary circumstances, such arrangements would be stable, but the magnetic pressure of a magnetar is so overwhelming that it constantly strains these structures. The crust essentially lives on the edge of failure, where small perturbations or shifts in the internal magnetic field can trigger massive cracks. These cracks propagate almost instantly, releasing vast amounts of energy and causing the surface to quake in a display of cosmic violence. Starquakes on a magnetar are not merely seismic events confined to the crust. They also have profound consequences for the surrounding magnetosphere. As the crust shifts and fractures, it twists the magnetic field lines extending outward from the star, injecting enormous amounts of energy into the magnetosphere. This energy can accelerate charged particles to near light speeds, generating streams of X-rays and gamma rays that escape into space. Observers across vast distances can detect these bursts, sometimes from tens of thousands of light years away. In extreme cases, such as the 2004 giant flare from SGR 1806-20, a single event can release more energy in a tenth of a second than our Sun emits in 100,000 years. The magnetar's crust, therefore, is not just a passive surface. It is an active, dynamic participant in some of the most energetic phenomena in the universe. The extreme density and instability of the crust also contribute to the short lifespan of a magnetar's intense magnetic activity. The crust acts as a mediator between the magnetic field and the stellar interior, gradually dissipating energy through these seismic events and radiation bursts. Unlike ordinary stars that can maintain a steady state for billions of years, the magnetar's surface is in a constant state of flux, constantly stressed by the magnetic field and relieved through episodic starquakes. This instability, while destructive, is what makes magnetars observable in the first place. Without it, their magnetic fields might remain hidden, and they would blend into the population of ordinary neutron stars. Furthermore, the crust's violent behavior also provides a unique laboratory for studying matter under conditions that cannot be replicated on Earth. In the extreme pressures and magnetic environments of a magnetar, atomic nuclei behave differently. Electron degeneracy is pushed to its limits, and even the quantum properties of matter become significant. Starquakes allow scientists to probe these conditions indirectly, using the resulting bursts of X-rays and gamma rays to infer the internal structure and properties of the crust. Each quake tells a story of matter under unimaginable stress, of forces so strong that they bend not just atoms, but the very fabric of space-time in the star's immediate vicinity. The surface of a magnetar is, therefore, a realm of pure violence. It is a landscape defined by ultra-dense matter, twisted and strained by incomprehensibly strong magnetic fields, constantly on the brink of rupture. Starquakes are a natural consequence of this instability, sending ripples of energy across the crust and into space, manifesting as some of the most powerful bursts of radiation in the cosmos. In essence, the magnetar's surface is both its signature and its engine, where the interplay of density, stress, and magnetic force creates a spectacle of destruction and light that is unique in the universe. The star's exterior is a window into the extremes of physics, a violent reminder of the destructive and creative power contained within the rarest stars in existence. The violent and unstable surface of a magnetar inevitably gives rise to one of its most awe-inspiring phenomena, starquakes. These events are the magnetar equivalent of earthquakes, but unlike anything experienced on Earth, they release staggering amounts of energy in an instant, illuminating the star and surrounding space with bursts of X-rays and gamma rays that are detectable across vast cosmic distances. To understand the scale of these starquakes, it is essential to recall the immense forces acting on a magnetar. The magnetic field alone, reaching quadrillions of times the strength of Earth's, constantly exerts pressure on the star's dense iron-like crust. This pressure twists and distorts the crust, creating immense tension over vast regions of the star's surface. Eventually, the stress becomes too great for the brittle crust to sustain, and it fractures suddenly, unleashing energy that would dwarf anything produced by ordinary stars. In many cases, a single starquake can release more energy in a fraction of a second than our Sun produces in 100,000 years. Starquakes occur because the magnetar's magnetic field is not uniform. It is highly dynamic and can shift over time. These shifts can induce sudden realignments in the crust, much like tectonic plates moving along faults on Earth. The difference is the scale. A magnetar's crust is under pressures so immense that these plates are essentially solid nuclear matter, and the shifts involve a mass and energy far beyond terrestrial comparison. When a starquake occurs, it not only fractures the crust, but also propagates seismic waves through the star's interior. These waves can interact with the magnetar's magnetic field, twisting and reconnecting magnetic lines in a process analogous to magnetic storms on Earth, but on a scale billions of times more intense. The combination of seismic motion and magnetic energy release produces the high-energy bursts that define magnetars as some of the most powerful phenomena in the universe. These bursts, often called giant flares, when they reach their peak intensity, are capable of temporarily outshining an entire galaxy. For example, in 2004, the magnetar SGR 1806-20 emitted a flare so powerful that it briefly became the brightest source in the Milky Way, despite being located roughly 50,000 light-years away. The energy released in this event was equivalent to the Sun's total energy output over 100,000 years, all released in less than a second. The flare's intensity was so great that it affected the Earth's ionosphere, even at this immense distance, demonstrating the raw power these stars can wield. While smaller flares and bursts are more common, the giant flares are a testament to the potential of starquakes to convert the internal magnetic and elastic energy of the crust into radiation with devastating efficiency. Interestingly, not all starquakes are equal. The magnitude and frequency of a magnetar's quakes are influenced by several factors, including the age of the star, the configuration of its magnetic field, and the state of its crust. Younger magnetars tend to have more unstable magnetic fields, leading to more frequent and sometimes more violent quakes. As a magnetar ages, the magnetic field slowly decays, and the frequency of these events decreases, although the crust remains capable of producing sudden, extreme flares. Observing the timing and energy of these starquakes provides astronomers with critical insights into the internal dynamics of magnetars, helping to inform models of their magnetic field evolution, crust composition, and the physical limits of ultra-dense matter. The energy bursts produced by starquakes are not confined to the immediate vicinity of the star. As the crust fractures and the magnetic field rearranges, enormous amounts of energy are released into the magnetosphere, accelerating charged particles to near light speeds. These particles emit X-rays, gamma rays, and sometimes even radio waves, which can travel vast distances across the galaxy. In some cases, these bursts may also contribute to phenomena such as fast radio bursts, FRBS, mysterious, millisecond-long flashes of radio waves detected from distant galaxies. While the connection between magnetars and FRBS is still an active area of research, observations of nearby magnetars producing both high-energy bursts and radio emission provide compelling evidence that starquakes could be responsible for some of these enigmatic signals. The study of starquakes also provides insight into the limits of physical laws under extreme conditions. In the high-density, high magnetic pressure environment of a magnetar's crust, matter behaves in ways that defy conventional physics. Atomic nuclei are distorted, electrons are constrained along magnetic field lines, and the normal rules governing the propagation of seismic waves are altered. This makes magnetars natural laboratories for studying phenomena that cannot be replicated in Earth-based laboratories, from the behavior of matter at supranuclear densities to the interaction of magnetic fields with ultra-dense solids. Each observed starquake is not just an event of spectacular energy release. It is a window into physics at the edge of human understanding. Starquakes also demonstrate that magnetars are not static objects. They are highly dynamic, living systems with internal stresses that build, shift, and release in complex cycles. In some models, these cycles are linked to the slow decay of the magnetic field. As the field gradually weakens, energy stored in the crust is episodically released through quakes. In others, the presence of small-scale magnetic instabilities or internal currents can trigger sudden, unpredictable fractures. This unpredictability is part of what makes magnetars so fascinating and dangerous, at least hypothetically, as their energy releases are not easily forecasted and can affect environments across vast distances. The combination of crustal instability, magnetic field stress, and energy release defines the magnetar as one of the most extreme and active types of stars in existence. Ultimately, starquakes and their resulting energy bursts are a vivid reminder of the incredible power contained within these rare cosmic monsters. From the crust's nuclear pasta lattice to the quadrillion Gauss magnetic fields that twist and strain it, every element of a magnetar is tuned to produce sudden, violent, and awe-inspiring displays of energy. They remind us that even in a galaxy filled with billions of ordinary stars, there exist a few exceptional, almost alien objects whose sheer energy and instability can reach across the void, announcing their presence to anyone watching, anywhere in the universe. The magnitude of these bursts puts the scale of the cosmos into perspective, showing that even the mightiest processes on Earth are but a fraction of the violence and energy continuously at work on a galactic scale. The immense energy unleashed by starquakes occasionally manifests in what can only be described as the most powerful explosions ever detected in the universe, and no event exemplifies this better than the 2004 giant flare from the Magnetar SGR 1806-20. This single outburst stands as a testament to the sheer destructive potential of magnetars and provides a glimpse into forces that far surpass anything experienced in the ordinary cosmos. On December 27, 2004, astronomers detected a burst of gamma rays so intense that it briefly became the brightest source in the Milky Way, despite originating roughly 50,000 light-years away. In mere tenths of a second, this flare released more energy than the Sun produces over 100,000 years, illuminating the surrounding galaxy and even impacting Earth's upper atmosphere, causing measurable disturbances in the ionosphere. To witness such a phenomenon is to confront the unimaginable scale of energy stored within a magnetar and the extraordinary consequences of a sudden magnetic rearrangement or catastrophic crustal shift. The SGR 1806-20 flare was so powerful that detectors across the world, and even instruments not designed for gamma-ray observation, registered its effects. Satellites designed to monitor the Sun were briefly blinded by the intensity of the gamma rays, demonstrating that a single magnetar event can surpass the energy output of hundreds of billions of stars combined, at least momentarily. Scientists theorize that this giant flare was triggered by a massive starquake, which released pent-up stress accumulated over decades in the magnetar's crust. The quake likely twisted and reconnected the star's magnetic field lines in a violent magnetic storm, converting the energy stored in the field into electromagnetic radiation and particle acceleration. The flare produced a main spike of gamma rays lasting about 0.2 seconds, followed by a decaying tail that persisted for several minutes as the star continued to oscillate and release energy. The implications of this event extend far beyond the magnetar itself. For one, the energy emitted in the flare could, if a magnetar were located much closer to Earth, have catastrophic effects on our planet. While SGR 1806-20 was safely tens of thousands of light-years away, a similar flare within even a few light-years could strip away the ozone layer, disrupt the atmosphere, and irradiate the surface with lethal doses of high-energy radiation. This scenario underscores the raw power of magnetars and why they are considered one of the rare yet potentially universe-altering objects in the cosmos. It also emphasizes the importance of understanding magnetars as part of the galactic environment, since their bursts are not just localized events, but phenomena capable of influencing interstellar space across tens of thousands of light-years. Another fascinating aspect of the SGR 1806-20 flare is its contribution to the study of extreme physics. Observing such an explosion allows scientists to test theories about the behavior of matter under conditions that cannot be replicated on Earth. The gamma-ray spectra, timing, and intensity provide clues about the interaction between the magnetar's magnetic field and its crust, the propagation of starquake-induced waves through ultra-dense nuclear matter, and the acceleration of particles in one of the most extreme magnetospheres known. In essence, each giant flare acts as both a natural experiment and a cosmic warning, revealing the enormous energies locked inside these exotic stars and the violent processes that release them. The SGR 1806-20 event also highlighted the rarity of such flares. While magnetars frequently produce smaller bursts of X-rays or gamma rays, a flare of this magnitude is extraordinary and occurs only a few times in a magnetar's lifetime. The statistical scarcity of giant flares underscores the uniqueness of SGR 1806-20's outburst and reinforces the perception of magnetars as not only rare, but also highly dynamic and unpredictable. Each flare reshapes our understanding of these stars, providing critical observational data that informs models of magnetic field decay, crustal composition, and high-energy radiation mechanisms. The fact that such an explosion can be observed across tens of thousands of light-years also emphasizes the observational advantages magnetars provide, allowing astronomers to study extreme physics on a galactic scale in real time. Moreover, the flare from SGR 1806-20 was a pivotal event in linking magnetars to other cosmic phenomena. Some researchers have suggested that giant flares from magnetars may be responsible for certain types of short gamma-ray bursts, GRBS, observed in distant galaxies. The temporal and spectral characteristics of the SGR 1806-20 flare resemble those of these mysterious GRBS, suggesting that magnetars, despite their rarity, may contribute significantly to some of the universe's most energetic and enigmatic explosions. This connection adds another layer of significance to the study of SGR 1806-20, as it provides a nearby laboratory to understand processes that may occur billions of light years away. The 2004 giant flare serves as a stark reminder of the violent potential contained within magnetars. It illustrates the magnitude of energy release possible from a single star, demonstrates the interconnectedness of magnetic fields, crustal stress, and energy bursts, and emphasizes the observational importance of these rare stars. SGR 1806-20, for those brief moments, outshone every other star in the Milky Way, asserting its presence across the galaxy and giving astronomers a rare glimpse into the extremes of stellar physics. Its flare was not merely an isolated spectacle. It was a cosmic demonstration of the forces that shape matter, magnetism, and energy under conditions beyond ordinary comprehension. In studying such events, we not only witness the power of magnetars, but also gain insight into the violent mechanisms that drive some of the universe's most extraordinary phenomena. The story of a magnetar's life is as fleeting as it is extraordinary. While ordinary stars like our Sun can shine steadily for billions of years, magnetars exist in a far more accelerated, intense, and violent state. From the moment of their birth in a cataclysmic supernova, magnetars are infused with immense rotational energy and magnetic fields that are orders of magnitude stronger than any other known star. These extreme conditions make them luminous, dynamic, and detectable across vast distances, but they also come at a cost. Magnetars burn through their magnetic energy at a staggering rate, causing their most extraordinary characteristics to last only a brief cosmic instant. On average, a magnetar remains in its highly magnetic, active phase for roughly 10,000 years, an almost imperceptible fraction of the Milky Way's lifespan, which is measured in billions of years. This brief lifespan is a direct consequence of the magnetar's extreme internal energy. The quadrillion Gauss magnetic field exerts continuous stress on the star's crust, driving repeated starquakes and bursts of high-energy radiation. Every flare, every release of X-rays or gamma rays represents a minute depletion of the energy stored in the magnetic field. Unlike ordinary neutron stars, whose magnetic fields are relatively stable over millions or even billions of years, magnetars dissipate their magnetic energy quickly because their fields are so intense that the forces they generate act almost like a built-in accelerator for energy release. This rapid consumption of magnetic energy not only powers the dramatic flares, but also dictates the brief window during which the magnetar can exhibit its most extreme behaviors. Once this energy diminishes, the star's magnetic field weakens, the frequency and intensity of bursts decrease, and the magnetar gradually transitions into a more conventional neutron star. The life cycle of a magnetar can be roughly divided into several stages. Initially, the newly formed magnetar rotates extremely rapidly, with spin periods measured in milliseconds. Its magnetic field is at its peak strength, and the star is highly unstable, prone to frequent and sometimes catastrophic starquakes. During this active youth, the magnetar releases immense bursts of energy, feeding both the electromagnetic radiation we observe and the high-energy particle acceleration in its magnetosphere. As the magnetic field slowly decays over thousands of years, the crust stabilizes somewhat, and starquakes become less frequent and less powerful. The energy output decreases correspondingly, and the star gradually fades from its status as a cosmic powerhouse to a quieter, less extreme neutron star, still dense and compact, but no longer capable of the dramatic outbursts that made it unique. One reason magnetars are so ephemeral is the interplay between magnetic field decay and rotational slowdown. Newly formed magnetars often spin hundreds of times per second, but the enormous magnetic field exerts a torque that gradually drains rotational energy, slowing the star down. This process, known as magnetic braking, contributes further to the decay of the magnetic field over time. Once the rotation slows and the field weakens, the star can no longer sustain the extreme conditions required to generate giant flares or maintain rapid, violent starquakes. In other words, the very forces that make magnetars spectacular are also the forces that burn them out quickly. Their lives are brilliant, chaotic, and short-lived, a fleeting flash of extreme physics in a galaxy of slower, steadier stars. The brevity of a magnetar's life also underscores why they are so rare and why only a handful are known in the Milky Way. Because the highly magnetic phase lasts just 10,000 years, there are only ever a small number observable at any given time. While billions of stars may exist in the galaxy, and tens of millions of neutron stars linger silently after supernovae, only around 30 magnetars have been confirmed. Many potential magnetars have either already burned out, their magnetic fields decayed into ordinary neutron stars, or have yet to be detected. This transient nature highlights that discovering a magnetar is akin to catching a cosmic lightning bolt in a bottle. They are not only rare in formation, but also fleeting in observable existence. Interestingly, the short lifespan of magnetars does not diminish their influence. Even in their brief lives, they contribute significantly to the galaxy's energetic environment. Giant flares like that of SGR 1806-20 starquakes and smaller bursts of radiation inject high-energy particles into the surrounding space, potentially influencing star formation in nearby regions and contributing to cosmic phenomena such as fast radio bursts. Despite existing for only 10,000 years, a magnetar leaves an indelible mark on its surroundings, a cosmic footprint that persists long after the star has transitioned into a quieter state. Ultimately, the lifespan of a magnetar illustrates both the brilliance and the impermanence of extreme objects in the universe. Their existence is a cosmic paradox. They are among the rarest and most energetic stars known, yet they are also fleeting, vanishing from their highly active phase almost as quickly as they appear. This ephemeral nature, combined with the incredible power they wield during their short lives, reinforces the sense of awe and wonder that magnetars inspire. They are a reminder that in the vastness of the universe, some of the most extraordinary phenomena are not only rare, but also transient, burning bright and violent for only the briefest moment in cosmic time. The fleeting lifespan of magnetars is intimately connected to their extreme rarity, a rarity that begins with the delicate and highly specific conditions required for their formation. Not every massive star that explodes as a supernova will give rise to a magnetar, and this selectivity is a product of both stellar physics and cosmic chance. Current theories suggest that only stars within a very narrow mass range, roughly between 20 and 40 times the mass of our Sun, possess the potential to become magnetars. Stars lighter than this threshold simply do not have the core density or the energy reserves necessary to produce a quadrillion Gauss magnetic field upon collapse, while stars more massive than this are likely to collapse directly into black holes, bypassing the neutron star stage entirely. This narrow mass window alone drastically limits the potential population of magnetars in any galaxy. However, mass alone is not enough. Rotation plays a critical role in the birth of a magnetar. Stars that spin rapidly in their final stages of life can generate powerful magnetic dynamos during core collapse, amplifying magnetic fields to extraordinary levels. If the star rotates too slowly, the dynamo effect is insufficient, and the resulting neutron star, while still extremely dense, lacks the extreme magnetism required to be classified as a magnetar. Conversely, if the rotation is too fast without other stabilizing conditions, the core may fragment or fail to form a coherent neutron star, possibly producing a more exotic outcome. Thus, the progenitor star must not only be massive enough, but also possess just the right combination of angular momentum and internal turbulence to generate the extraordinary magnetic field that defines a magnetar. Metallicity, the abundance of elements heavier than hydrogen and helium in a star, also influences the likelihood of magnetar formation. Stars with low metallicity retain more mass and angular momentum over their lifetimes because they experience weaker stellar winds. In contrast, high metallicity stars lose significant mass and rotational energy through powerful stellar winds, reducing the likelihood that they will maintain the rapid rotation necessary to produce a magnetar. Observations support this connection, suggesting that magnetars are more likely to originate in regions of the galaxy with lower metallicity, highlighting how both intrinsic and environmental factors play into their rarity. Another factor contributing to their scarcity involves the mechanics of the supernova explosion itself. Not all supernovae are symmetric, and the formation of a magnetar may require a particular degree of asymmetry in the explosion. The orientation, speed, and distribution of the ejected material influence the proto-neutron star's rotational dynamics and internal turbulence, both of which are crucial for the magnetic field amplification. Small differences in the supernova process can mean the difference between producing a regular neutron star or the ultra-rare magnetar. In this sense, magnetars are the cosmic equivalent of winning the lottery. Not only do the initial conditions need to be just right, but the collapse itself must unfold in a highly specific manner. Even after formation, the survival of a magnetar in its highly magnetic, observable state is limited. The extreme magnetic field, while defining, also ensures that the magnetar's life is extraordinarily brief on cosmic timescales. Many progenitor stars that might have had the potential to form magnetars produce neutron stars whose magnetic fields decay more slowly or whose rotations are insufficient, meaning that at any given time only a handful of magnetars exist in a galaxy filled with billions of stars. This combination of highly selective formation conditions and rapid magnetic decay ensures that magnetars remain among the rarest and most enigmatic stellar objects known to science. Interestingly, these constraints may explain why magnetars are so localized in certain regions of the galaxy. Astronomers have noted that many known magnetars are found in star-forming regions or near clusters of massive stars, where the conditions for their progenitors, low metallicity, high mass, and rapid rotation, are more likely to coincide. Yet even in these fertile environments, only a tiny fraction of stars achieve the precise conditions needed, underscoring the delicate balance required to produce a magnetar. This scarcity, coupled with their brief lifespans, ensures that the population of magnetars is exceptionally small. While billions of stars exist in the Milky Way, Only about 30 have been confirmed as magnetars, highlighting just how extraordinary these cosmic phenomena are. Beyond their formation, magnetars also contrast sharply with other neutron stars, such as pulsars. While pulsars are numerous and widespread, forming from a broader range of progenitor masses and rotational conditions, magnetars occupy a far narrower parameter space. This explains why, even among neutron stars, already a relatively rare class, magnetars stand out as exceptional. They are not merely unusual. They represent the extreme tail of a very specific distribution, existing only where mass, rotation, metallicity, and collapse conditions all align perfectly. Their rarity is a combination of cosmic selection and physical inevitability. Only under these precise conditions can a star reach the extreme magnetic intensity and violent energy release that define a magnetar. In short, the scarcity of magnetars is a product of extraordinarily specific requirements. Only stars with just the right mass, rotational velocity, metallicity, and supernova dynamics can give rise to them. Even then, the magnetic fields that make them extraordinary also ensure that their lives are short, leaving only a handful visible at any given time. This combination of precise formation conditions and brief lifespans makes magnetars among the rarest objects in the universe, cosmic anomalies whose existence illuminates the delicate balance of forces and conditions that govern stellar evolution. They are not only rare by chance, they are rare by the very laws of physics themselves, standing as singular testaments to the extremes of the universe. While magnetars are extraordinary for their immense magnetic fields and explosive energy releases, they are closely related to another class of neutron stars known as pulsars. Both magnetars and pulsars emerge from the violent deaths of massive stars, and both share the common traits of extreme density and rapid rotation. Yet, despite these similarities, the two types of neutron stars represent remarkably different evolutionary paths, shaped by variations in magnetic field strength, rotational properties, and internal dynamics. Understanding the contrast between them illuminates not only the diversity of neutron stars, but also the unique place of magnetars as cosmic anomalies. Pulsars are perhaps the more familiar of the two, discovered in 1967 through their precise, periodic emissions of radio waves. These emissions are the result of a misalignment between the pulsar's magnetic axis and its rotational axis. As the star spins, its magnetic poles sweep beams of electromagnetic radiation across space, much like a lighthouse beam. If Earth lies in the path of these beams, we observe them as regular pulses, often with astonishing precision that rivals atomic clocks. The magnetic fields of pulsars, though extraordinarily strong by terrestrial standards, typically on the order of 10 to the 8th to 10 to the 12th Gauss, pale in comparison to the quadrillion Gauss fields of magnetars. While pulsars are known for their regularity and reliability, their energy output is generally steady, lacking the sporadic and violent flares characteristic of magnetars. Magnetars, on the other hand, occupy the extreme end of the neutron star spectrum. Their magnetic fields are not merely stronger, they dominate the star's behavior, shaping everything from the crust's structure to the surrounding magnetosphere. While a pulsar's emissions are defined by rotation and geometry, a magnetar's emissions are often dominated by episodic bursts caused by magnetic field instabilities and starquakes. These bursts can be thousands or millions of times more energetic than the regular pulses of a typical pulsar, producing high-energy X-rays and gamma-rays rather than the steady radio waves for which pulsars are known. In effect, while pulsars act like cosmic metronomes, magnetars behave like volatile cosmic dynamos, releasing sudden and unpredictable bursts of energy that can outshine entire star clusters for brief moments. The difference in behavior between pulsars and magnetars can also be traced back to their formation. Both emerge from the collapse of massive stars, but the progenitors of magnetars are typically more massive, spin faster, or possess other conditions that favor the amplification of magnetic fields to the extreme levels necessary to classify the star as a magnetar. In contrast, the majority of neutron stars born in supernovae become pulsars because their rotation and magnetic field conditions fall within a more common range. This distinction explains why pulsars are far more numerous than magnetars. While the Milky Way contains thousands of observed pulsars, only around 30 magnetars have been confirmed. The rarity of magnetars, combined with their short active lifespan, makes them far less common and highlights the specific circumstances required for their formation. Another point of contrast lies in observational characteristics. Pulsars are typically detected through their radio emissions, which are stable, periodic, and predictable. Their pulses can be so precise that astronomers use them as cosmic clocks to study gravitational waves, test general relativity, and even navigate spacecraft. Magnetars, in contrast, are primarily detected through their high-energy X-rays and gamma-ray bursts. These bursts are sudden, intense, and often unpredictable, making magnetars more challenging to observe and study over time. In some cases, magnetars also produce transient radio emissions, particularly following giant flares or starquakes, but these signals are irregular and typically short-lived, in stark contrast to the rhythmic pulses of ordinary pulsars. The contrast between the two also highlights differences in energy reservoirs and decay mechanisms. A pulsar's energy comes primarily from rotational kinetic energy. Over millions of years, pulsars gradually spin down, losing energy at a steady rate. Their magnetic fields, while strong, decay slowly, allowing pulsars to remain observable for tens or hundreds of millions of years. Magnetars, by contrast, are powered largely by magnetic energy. Their fields are so intense that they decay rapidly, driving frequent and sometimes catastrophic bursts of radiation. This explains why magnetars are not only rarer, but also have much shorter observable lifespans than pulsars, burning brightly for just a few thousand years before transitioning into quieter neutron stars. Despite these differences, magnetars and pulsars share an underlying connection as neutron stars, remnants of stellar cores compressed to densities surpassing anything achievable on Earth. They both exhibit extreme gravitational fields, exotic states of matter, and rapid rotation, providing scientists with invaluable natural laboratories for studying physics under conditions impossible to replicate in terrestrial experiments. Where they diverge is in how these extreme properties manifest. Pulsars showcase regularity, precision, and the predictable sweep of electromagnetic beams, while magnetars reveal volatility, immense magnetic dominance, and episodic bursts of energy that redefine our understanding of stellar extremes. In summary, pulsars and magnetars are two faces of the neutron star phenomenon. Pulsars are numerous, regular, and reliable, with emissions governed by rotation and modestly extreme magnetic fields. Magnetars, by contrast, are rare, short-lived, and violent, dominated by magnetic fields so powerful they distort matter itself and drive sudden, intense energy releases. This contrast not only emphasizes the extraordinary nature of magnetars, but also provides a framework for understanding the diversity of outcomes when massive stars collapse. It is a vivid demonstration of how small differences in mass, rotation, and internal dynamics can produce radically different cosmic objects, each remarkable in its own right. The extraordinary power of magnetars extends far beyond their immediate stellar neighborhoods, and one of the most intriguing connections lies between magnetars and gamma-ray bursts, GRBS, some of the most powerful explosions in the universe. GRBs are brief but intensely energetic flashes of gamma radiation observed from distant galaxies, capable of releasing in seconds the energy our Sun emits over billions of years. They are divided into two categories: long-duration bursts, typically associated with collapsing massive stars, and short-duration bursts, which last less than 2 seconds and have long puzzled astronomers regarding their precise origins. Recent research suggests that magnetars, particularly newly formed or highly stressed ones, may be responsible for at least a portion of these short gamma-ray bursts, providing a fascinating link between some of the universe's rarest stars and its most extreme energetic events. The mechanism connecting magnetars to short GRBs involves both the birth and death of these stellar giants. When a massive star collapses into a magnetar, the rapid rotation and extreme magnetic field can produce conditions ripe for an initial burst of energy. This can include the formation of relativistic jets, narrow beams of matter, and radiation traveling close to the speed of light. These jets, aligned with the star's magnetic axis, can escape into space if the surrounding material from the supernova allows. For observers aligned with these jets, the release appears as an extraordinarily bright and brief gamma-ray flash, a short GRB. The energy of such an event is staggering. It can outshine the combined light of billions of stars, all concentrated in a fleeting burst lasting only milliseconds to seconds. The connection suggests that the same forces that drive magnetar flares, rapid magnetic reconnection, rotational energy, and crustal instability, may also underlie these brief but immensely powerful cosmic explosions. Moreover, theoretical models indicate that magnetars formed in binary neutron star mergers could be particularly potent progenitors of short GRBs. When two neutron stars collide, the result may not be an immediate black hole, but a hypermassive, rapidly spinning magnetar. This newborn magnetar can have magnetic fields reaching or exceeding 10 to the 15th Gauss, and the extreme rotational energy can power relativistic jets that produce gamma rays observable across billions of light years. In these cases, the short GRB represents not just a single burst, but a window into the physics of a star at the very edge of stability, where rotation, magnetic stress, and nuclear density converge to create one of the universe's most violent phenomena. Observational data from satellites such as NASA's Swift and Fermi have detected short GRBs with afterglow emissions consistent with magnetar models, providing indirect evidence supporting this connection. Even outside of binary mergers, isolated magnetars can contribute to short gamma-ray bursts through extreme starquakes or magnetic instabilities. In this scenario, the sudden rearrangement of the star's magnetic field releases enormous amounts of energy in a very short time. The reconnection of magnetic field lines can accelerate particles to near light speeds, producing a concentrated burst of gamma rays. While these bursts are less common and typically less energetic than those associated with mergers, they nonetheless demonstrate the potential of magnetars to generate some of the most powerful explosions known. Their rarity, combined with the brief window of high magnetic activity, explains why only a small fraction of GRBS can be confidently linked to magnetars, yet the theoretical framework strongly supports the connection. The study of magnetar-associated GRBS also sheds light on the broader understanding of cosmic explosions. By analyzing the temporal profiles, spectral signatures, and afterglow emissions of short GRBs, astronomers can infer properties of the progenitor magnetar, such as its magnetic field strength, rotational period, and the energy released during the collapse or flare. In some observed events, the decay of the gamma-ray emission follows patterns consistent with the gradual slowdown of a rapidly rotating magnetar, providing further evidence that these stars play a role in driving some of the universe's most intense radiation events. Magnetars, in this sense, act as both engines and laboratories, offering a natural setting to study physics under conditions impossible to replicate on Earth. Beyond the energy released, the connection between magnetars and short GRBs has profound implications for understanding the life cycles of stars and the evolution of galaxies. Each short GRB, potentially linked to a magnetar, marks the end of a highly specific and rare stellar process. The collapse of a massive star under just the right conditions, or the merger of two dense neutron stars to form a hypermagnetized object. These events not only produce detectable gamma radiation, but can also seed the surrounding interstellar medium with heavy elements and energetic particles, influencing star formation and galactic evolution over time. Magnetars, therefore, are not just rare cosmic curiosities. They are active participants in shaping the universe on large scales, their fleeting lives producing bursts of energy that echo across billions of light years. In summary, magnetars provide a plausible explanation for at least some short gamma-ray bursts, linking the extreme magnetic fields and rapid rotations of these stars to some of the most energetic events ever observed. Whether through birth in supernovae, violent starquakes, or post-merger hypermagnetization, magnetars create conditions that can generate gamma rays intense enough to rival entire galaxies. By studying these connections, scientists gain insights not only into the physics of magnetars themselves, but also into the broader dynamics of cosmic explosions, star formation, and the energetic evolution of the universe. The role of magnetars in short GRBs underscores their status as both rare and consequential, demonstrating that even in their brief lifespans, these stars leave an outsized impact on the cosmos. The strange story of magnetars grows even more fascinating when we look at another cosmic enigma: fast radio bursts, FRBs. These are incredibly brief, millisecond-long flashes of radio waves that originate from distant galaxies. For years, their origin was one of the biggest mysteries in astrophysics. Some appeared only once, while others repeated sporadically, leaving astronomers puzzled about what could possibly generate such powerful signals in such a short time. To put their energy into perspective, in just a few milliseconds, an FRB can release as much energy as the Sun emits in several days. Detecting them requires precise, fast instruments because they vanish almost as quickly as they arrive, like a cosmic whisper amplified to deafening volume before fading into silence. At first, theories about FRBs ranged from exotic astrophysical processes to the possibility of alien technology, since their signals were so sudden, bright, and unusual. But over time, one natural explanation rose to the top: magnetars. Given their intense magnetic fields and violent flaring activity, they seemed like prime candidates for generating bursts of radio waves powerful enough to travel across the universe. The key link came in 2020, when astronomers observed a magnetar in our own galaxy, SGR 1935 plus 2154, emitting a radio burst so bright and so brief that it matched the same pattern as FRBs seen in distant galaxies. For the first time, the connection was no longer speculative. It was real evidence that magnetars could indeed produce FRB-like signals. The mechanism behind this is thought to involve magnetic reconnection and starquakes on the magnetar's surface. When the magnetic field lines become twisted and snap, or when the crust shifts under immense pressure, a sudden release of energy occurs. This energy doesn't just create gamma rays and X-rays, it can also accelerate charged particles, producing coherent bursts of radio waves that escape into space as an FRB. In some cases, these bursts are accompanied by X-ray flares, suggesting a direct physical connection between magnetar activity and multi-wavelength emissions. The fact that we have now observed this in our own galaxy strengthens the idea that at least some, and perhaps many, of the mysterious FRBs seen across the universe, are born from the violent hearts of magnetars. Yet, the story is not entirely solved. While magnetars are an excellent explanation for some FRBS, not all of them fit the same mold. For instance, some FRBS repeat over time with varying intensity and frequency, while others appear as single, non-repeating flashes. Magnetar models can account for both scenarios. Repeating FRBs could come from ongoing starquake activity in a restless magnetar, while one-off bursts might result from catastrophic events like a massive flare or collapse. But the variety in FRB behavior suggests that magnetars might not be the only sources. Still, the magnetar connection has opened a crucial doorway, giving astrophysicists a testable framework that aligns with real observations. Another fascinating aspect is the sheer distance FRBS can travel. Many FRBs originate billions of light years away, meaning the signals we detect today began their journey long before Earth even existed. For a magnetar's flare to remain detectable across such unimaginable distances, the energy involved must be staggeringly high, reinforcing the idea that magnetars are among the few astrophysical objects capable of generating them. This makes FRBS not only intriguing mysteries, but also powerful tools for probing the large-scale structure of the universe. By studying how FRB signals are dispersed as they pass through intergalactic plasma, scientists can measure properties of the cosmic web itself, essentially using magnetar flares as natural beacons to map the universe. The link between magnetars and FRBS also deepens our understanding of how diverse the manifestations of these stars can be. On one hand, they create bursts of gamma rays that can rival the brightness of entire galaxies. On the other, they generate millisecond-long radio flashes that sweep across the cosmos like cosmic Morse code. Both extremes stem from the same underlying physics, the unstable marriage of nuclear density matter and magnetic fields a quadrillion times stronger than Earth's. That such a compact, short-lived star can affect the universe on this scale shows just how central magnetars are to some of the deepest astrophysical puzzles. In a way, FRBS are like cosmic fingerprints of magnetars, unique, fleeting, and immensely powerful. With each new detection, we inch closer to decoding not only the behavior of these rare stars, but also the fabric of space they illuminate. Future observatories, such as the Square Kilometre Array, are expected to detect thousands of FRBS per year, giving scientists a treasure trove of data to refine the magnetar connection further. Every new burst we catch could be the echo of a starquake or a magnetic storm on one of these elusive cosmic giants, offering a real-time glimpse into processes that otherwise remain locked deep inside their dense crusts. Thus, magnetars are not just stars of extremes, they may also be broadcasters of some of the universe's most mysterious signals. The confirmation of their role in FRBS links two of the cosmos's strangest phenomena together, showing once again how these rare objects punch far above their weight in terms of cosmic significance. The sheer violence of a magnetar's existence raises an unsettling question. What would happen if one of these cosmic monsters ever strayed too close to Earth? At their current distances, thousands to tens of thousands of light years away, magnetars are safe to study through telescopes. But the reality is that their power is so extreme that if a magnetar were located within just a handful of light years, our planet would be in grave danger. Unlike black holes, which consume matter only within their event horizon, magnetars pose a threat because of the sheer scale of radiation they release. Their bursts of X-rays and gamma rays are so intense that they could potentially strip away Earth's atmosphere and expose the surface to lethal levels of cosmic radiation. To put it into perspective, a single magnetar flare can outshine every other star in the Milky Way combined for a fraction of a second. If one of those bursts occurred just a few light years away, Earth's magnetic shield and ozone layer would likely be no match for it. The immediate effect would be a dramatic surge in ionizing radiation, which could dismantle the molecules in our atmosphere. Without the protective ozone, ultraviolet radiation from the sun would bombard the surface, sterilizing large swaths of the biosphere. Even if life somehow clung on, the long-term damage to the climate and ecosystems would be devastating. Magnetars, in this way, are cosmic reminders that not all threats come in the form of physical impacts. Sometimes, it's invisible waves of radiation that carry the greatest danger. Beyond the atmospheric destruction, there's also the matter of direct radiation. High-energy gamma rays from a nearby magnetar could penetrate deep into the planet's surface, disrupting DNA, breaking chemical bonds, and triggering mass extinctions. Scientists have speculated that some past extinction events in Earth's history might have been influenced by gamma-ray bursts or similar cosmic phenomena, though there is no direct evidence yet linking a magnetar flare to such events. Still, the possibility remains. After all, Earth has orbited the galaxy for over 4.5 billion years, and in that time, it has likely crossed paths with stellar remnants of all kinds. Another chilling aspect of magnetars is their magnetic reach. A magnetar's field, though it weakens with distance, could extend far enough to influence the magnetic balance of planets nearby. If a magnetar were to pass within a few light years, its magnetic power might disrupt satellites, electronics, and even biological systems sensitive to magnetism. Theoretically, if one came close enough, say within a light year or two, its field could be strong enough to scramble atomic structures, distort chemical bonds, and potentially interfere with life at the molecular level. At that range, humans and all of Earth's technology would face an onslaught not just of radiation, but of a magnetic dominance unlike anything we can shield against. Fortunately, we are safe for now. The nearest known magnetar, XTEJ 1810-197, lies about 8,000 light-years away, far too distant to pose any threat to Earth. The universe, in its vastness, has scattered these objects thinly enough that the chances of one drifting dangerously close to us in the near future are astronomically small. But the fact that they exist, and that their potential for destruction is so absolute, is enough to keep them on the list of cosmic doomsday scenarios. Astronomers continue to monitor magnetars for sudden flares, not just out of curiosity, but also because their radiation can affect spacecraft, satellites, and communication systems even at extreme distances. A truly powerful flare could wash across our solar system like a tidal wave of high-energy light, potentially disrupting power grids and satellites, even if it wasn't close enough to endanger life directly. In the grand scheme of cosmic hazards, magnetars are among the most terrifying, not because of their frequency, but because of the magnitude of devastation they could cause if proximity ever became an issue. They are like loaded cannons scattered across the galaxy, most of them far enough away that we can study them safely, but each one holding the power to annihilate a planet's habitability under the wrong circumstances. And yet, as with most of the universe's dangers, the very factors that make them a threat also make them endlessly fascinating. They are both destroyers and teachers, forcing us to confront how fragile our world really is when measured against the forces at play in the wider cosmos. Despite the terrifying destructive power magnetars could unleash if they were ever close, the truth is that these stellar beasts are not easy to spot in the first place. They don't shine like ordinary stars that dot our night sky. In fact, if you were to look up at the heavens with the naked eye, you would never see a magnetar, not because they aren't luminous, but because the type of energy they emit lies outside the visible spectrum. Where normal stars glow in optical light, magnetars announce their existence through pulses of X-rays and gamma rays, the most energetic forms of radiation in the universe. This means that astronomers rely not on traditional telescopes, but on specialized observatories orbiting Earth to detect them. The first clues to magnetars came not from planned observation, but from unexpected bursts of radiation that seemed to appear out of nowhere. In the late 20th century, satellites originally launched to monitor nuclear explosions on Earth's surface began detecting strange, repeating flashes of gamma rays from deep space. These mysterious signals were later linked to what we now know as magnetars. Their flares are so sudden and so intense that they stand out against the cosmic background, making them some of the brightest high-energy events detected in our galaxy. When a magnetar cracks or flares, it doesn't whisper, it shouts, and even though these outbursts may last only fractions of a second, they are powerful enough to be noticed from across the Milky Way. Astronomers now use an arsenal of space-based instruments to track magnetars. The Chandra X-ray Observatory, XMM Newton, NuSTAR, and NASA's Swift Observatory are just a few examples of satellites capable of catching their high-energy emissions. These telescopes are equipped with detectors sensitive to X-rays and gamma rays, allowing scientists to watch for sudden spikes of activity that indicate a magnetar has awakened. Sometimes, these instruments capture not just one burst, but a series of them, like aftershocks following an earthquake. Each signal gives researchers valuable information about the magnetar's spin rate, energy output, and magnetic field strength. Interestingly, many magnetars are discovered not during their quiet phases, but during these dramatic flares. A previously unknown neutron star might suddenly light up in X-rays, revealing its existence to astronomers who then turn other instruments to monitor it closely. Once detected, these objects can be studied over time as they rotate, emitting periodic X-ray pulses that allow scientists to measure their spin periods with incredible precision. Magnetars typically rotate once every 2 to 12 seconds, slow compared to most pulsars, but still unimaginably fast when you remember we're talking about a star the size of a city spinning endlessly in space. Ground-based radio telescopes have also joined the hunt. While most magnetars are radio quiet, a handful have been caught emitting radio waves during outbursts, blurring the line between them and pulsars. Instruments like the Parkes Observatory in Australia and the Green Bank Telescope in the US have detected such signals, helping to expand the catalogue of known magnetars. With the discovery that magnetars can produce fast radio bursts, radio astronomy has become even more critical in identifying and studying these rare stars. The upcoming Square Kilometre Array, the world's largest radio telescope currently under construction, promises to revolutionize our understanding by detecting thousands of high-energy bursts, some of which will almost certainly be magnetar-related. What makes magnetar detection particularly exciting is that every new discovery feels like unearthing a hidden gem in the galaxy. Out of hundreds of billions of stars, finding one of only a few dozen magnetars is akin to stumbling across a needle in a cosmic haystack. And each one behaves differently. Some are quiet for decades before erupting in a blinding flare, while others pulse steadily in X-rays, offering astronomers a rare chance to study them continuously. By piecing together these observations, scientists are slowly building a clearer picture of how magnetars form, evolve, and interact with their environment. This ability to track their outbursts and monitor their strange signals reminds us that even though magnetars are distant and rare, we are not powerless to study them. They leave fingerprints across the electromagnetic spectrum, And with each passing decade, our tools to read those cosmic signatures grow sharper. Magnetars may be elusive, but their eruptions are so loud in high-energy light that they cannot stay hidden forever. And some of the most famous ones we know today were all found through this careful detective work. These names may not sound poetic, but behind each is a story of extreme physics and violent eruptions that astronomers captured just in time. The fact that we know them at all is proof of how far human technology has come, giving us the power to detect stars that exist far beyond the realm of ordinary sight. Among the vast tapestry of stars in our galaxy, only a few stand out as the rarest of the rare, the known magnetars. These cosmic titans don't have names that roll off the tongue like Sirius or Betelgeuse. Instead, they're catalogued with designations like SGR 1806-20, 1E 1048.1-5937, and Swift J 1818.0-1607. Labels that reflect the satellites and instruments that first detected them. Yet behind these sterile-sounding names lie some of the most extreme and fascinating objects the universe has ever produced. Each magnetar tells a unique story, offering astronomers an irreplaceable chance to peek into the violent lives of these magnetic monsters. Take SGR 1806-20, perhaps the most infamous of all known magnetars. Discovered as a source of soft gamma rays, hence the SGR in its name, it sits roughly 50,000 light-years away in the constellation Sagittarius, near the galactic center. What makes it so legendary is the event of December 27, 2004, when it released a giant flare so powerful that it briefly outshone the entire Milky Way. For a fraction of a second, it was the brightest source of gamma rays in the sky, visible even to spacecraft orbiting Earth, despite its immense distance. That explosion was so intense that it saturated detectors and rattled Earth's ionosphere, demonstrating firsthand how even a far-off magnetar could influence our planet. SGR 1806-20 remains a benchmark in magnetar studies, showing just how violent and unpredictable these stars can be. Then there's 1E10 48.1-5937, a magnetar that resides in the Carina constellation, about 9,000 light-years from Earth. This particular magnetar has captivated scientists because of its erratic behavior. Unlike some that remain relatively quiet between outbursts, 1E1048.1-5937 experiences dramatic changes in brightness, spin rate, and X-ray emissions. It has undergone multiple outbursts since its discovery, sometimes surprising astronomers with sudden increases in X-ray luminosity that fade over weeks or months. These fluctuations provide valuable data on how magnetars release their magnetic energy over time, and why some experience repeated storms while others stay dormant for centuries. Its temperamental nature has made it something of a laboratory magnetar, giving us ongoing clues into the mechanics of magnetic fields and stellar crust activity. A newer entry to the catalogue is Swift J 1818.0-1607, discovered in 2020 by NASA's Swift Observatory. What makes this one extraordinary is that it is both young and unusually fast spinning for a magnetar. With an age estimated at just about 240 years, a blink of an eye in cosmic time, it may be the youngest magnetar ever observed. Its rotation period is about 1.36 seconds, making it the fastest spinning magnetar discovered so far. Normally, magnetars rotate more slowly than their pulsar cousins, but Swift J 1818.0-1607 is an exception, blurring the line between the two types of neutron stars. Its youth and speed make it invaluable to astronomers trying to understand how magnetars form immediately after a supernova, and how their magnetic fields evolve in their earliest stages. It's as if we've caught this one just after its birth cry, giving us a front-row seat to the beginning of a magnetar's violent life cycle. These three are only highlights from a very short list. Fewer than 35 confirmed magnetars exist in our galaxy, and each is unique. Some, like XTEJ 1810-197, have been observed switching on and off in radio frequencies, surprising astronomers by acting like pulsars for a time before quieting down again. Others, such as 4U0142+61, show strange infrared emissions that hint at debris disks, possibly the leftover material from their violent birth explosions. Every magnetar studied so far has added a new layer of mystery, reinforcing that no two behave exactly alike. For such a rare population, their diversity is staggering. What binds them together is their rarity and their extremes. Each one is a living paradox. A star so small it could fit inside a city, yet so powerful it can reshape the very matter around it. To find even a single magnetar in a galaxy of hundreds of billions of stars is remarkable, and to know of more than 24 is a testament to the relentless pursuit of astronomers scanning the heavens with specialized instruments. Each detection is not just another tick on a list. It's an invitation to explore a corner of physics that Earth can never replicate. But what makes these stars even more extraordinary is not only their rarity, but also the brevity of their existence in this extreme state. Unlike red dwarfs, which burn steadily for trillions of years, or even white dwarfs, which fade over billions, magnetars exist in their hypermagnetic form for only a fleeting moment in cosmic history. And that leads directly into the next realization. Their short lives are one of the key reasons why they are so elusive. For all their overwhelming power, their flares that can outshine galaxies, and their magnetic fields that defy human comprehension, magnetars are not built for longevity. In fact, one of the most defining features of these rarest stars is how briefly they shine in their extreme state. If red dwarfs are the universe's marathon runners, burning dimly but steadily for trillions of years, then magnetars are the sprinters, blazing through their short cosmic moment with intensity that leaves an indelible mark, before fading into quieter existences as ordinary neutron stars. Their short lives are a crucial part of why they are so rare, and understanding this fleeting stage provides an even deeper appreciation of their importance in the cosmic story. Magnetars typically remain in their ultramagnetic, flare-prone state for only about 10,000 years. On human scales, that seems incomprehensibly long. But in the language of stars, where lifespans are often measured in millions, billions, or even trillions of years, 10,000 is practically nothing. It's less than a blink in the galaxy's timeline. Stars, like our Sun, will burn hydrogen for 10 billion years before expanding into red giants. White dwarfs take billions of years to cool. Even pulsars, their neutron star cousins, can remain detectable for tens of millions of years as they slowly spin down. Magnetars, by contrast, live lives of brilliant intensity and then quickly transition into quieter, less exotic forms. Why are their lives so short? The answer lies in the very thing that makes them extraordinary: their magnetic fields. Magnetars begin existence with fields 1,000 times stronger than those of pulsars, reaching up to 10 to the 15th Gauss, a quadrillion times Earth's magnetic field. But those fields are unstable, burning through their energy reserves at an incredible rate. Unlike the stable fusion engines of main sequence stars, magnetars don't have a steady power source. Instead, they live on borrowed time, feeding off the stored magnetic energy wound tightly into their dense crusts and cores. Every flare, every starquake, every burst of gamma or X-rays is a release of that energy, slowly eroding the very force that defines them. Over the course of thousands of years, the magnetic field of a magnetar decays. The decay process itself may be violent, triggering bursts and flares, but the overall trend is inevitable. The field weakens. As it does, the star loses the defining features that make it a magnetar. Its once ferocious field settles into something closer to that of an ordinary neutron star, perhaps a pulsar, or eventually just a quiet, cooling remnant. In essence, a magnetar is not a permanent type of star, but rather a phase, a brief transitional state in the evolution of a neutron star born under just the right conditions. This ephemerality is why they are so hard to catch. Out of the countless supernovae that have exploded over the galaxy's history, many may have produced magnetars. But because their lifetimes as hypermagnetic beasts are so short, only a handful are still active today for us to observe. Consider this: our galaxy is more than 13 billion years old, and over that immense span of time, billions of massive stars have lived and died in supernovae. If even a small percentage of those collapses created magnetars, then the total number of magnetars that have ever existed in the Milky Way could number in the millions. Yet we only see about 30 today, because the vast majority have long since cooled, their magnetic fields having faded into obscurity. What we are observing now is not the total population, but only the few who still burn brightly in this fleeting stage. This realization reframes their rarity, not as a sign that they are almost never created, but that their window of visibility is so small that only a select few overlap with our moment in cosmic history. Their short lives also carry profound consequences for the environments around them. During their active magnetar phase, they unleash so much radiation and energy that they can dramatically alter their surroundings. A giant flare can ionize gas clouds, disturb nearby stars, and accelerate particles across interstellar space. But once the magnetar's energy fades, so does its influence. The once feared beast becomes just another quiet neutron star, indistinguishable from the countless stellar remnants that populate the galaxy. It's as if nature allows them one dramatic performance, a cosmic fireworks display, and then retires them into anonymity. Yet, even though magnetars fade quickly, their legacy endures. The bursts of energy they emit can leave permanent imprints on the interstellar medium. They may contribute to the formation of mysterious high-energy phenomena like fast radio bursts and short gamma-ray bursts, as we've explored earlier. They may also seed the galaxy with heavy elements forged in their violent births, enriching future generations of stars and planets. So while their extreme lives are brief, their effects ripple outward, influencing the galaxy for much longer than they remain active. In this way, magnetars are like shooting stars on a cosmic scale, brief, dazzling, and unforgettable, leaving behind changes that last long after they've dimmed. The short lifespan of magnetars also explains why they hold such a mythical place in astrophysics. Because we can only study them during this narrow time window, they become like rare fossils or fleeting natural events on Earth, phenomena that must be captured while they last, because they won't be around forever. Astronomers know that every magnetar flare observed could be the last one we see from that star, making each detection a precious opportunity. When a new magnetar is discovered, as in the case of Swift J1818.0-1607, which is barely 2 centuries old, it feels like a stroke of cosmic luck. We are peering into a phase of stellar life so rare and so brief that it's akin to witnessing a butterfly emerge from its cocoon, only to live for a single day. Their short lives, then, are both a blessing and a curse. A blessing because their violent bursts give us insights into physics under conditions we cannot replicate on Earth. A curse because the opportunities to study them are so few and far between. Each magnetar we observe is like a lighthouse in the darkness, but its light will eventually dim, leaving us with only memories and data to carry forward. It is this tension between rarity and brilliance, between fleeting existence and enduring mystery, that makes magnetars such compelling objects of study. And this brings us to a fundamental question. Why are magnetars so rare in the first place? Is it simply their short lifespan that makes them elusive? Or are there deeper reasons why only a small fraction of stars ever become magnetars at all? The answer lies in the peculiar circumstances of their birth, the thin balance of mass, rotation, and magnetic field amplification that makes these cosmic monsters possible. When we look at magnetars, we are not just gazing at another type of star. We are looking at cosmic laboratories, natural testing grounds where the laws of physics are pushed far beyond anything humans can reproduce on Earth. These stars are so extreme that they force our theories of matter, energy, and space-time to their breaking points, revealing what happens when nature amplifies the rules of physics to almost unimaginable levels. Magnetars are, in essence, windows into a realm of the universe where the familiar laws of reality begin to warp and entirely new insights emerge. On Earth, the strongest magnetic fields we can create in laboratories with advanced technology reach into the tens of thousands of Gauss, sometimes briefly into the millions with pulsed magnets. That's impressive compared to Earth's natural magnetic field, which hovers around 0.5 Gauss. But compared to a magnetar, our technological feats seem laughable. A magnetar's field can be as strong as 10 to the 15th Gauss, meaning a trillion times stronger than the strongest magnet ever built on Earth. These magnetic fields are not just powerful, they are transformative. They are strong enough to deform the very structure of atoms, squeezing electrons and protons into elongated cigar-like shapes. The familiar idea of atoms as little solar systems with orbiting electrons collapses under such pressure. In a magnetar's presence, matter itself is rewritten. This is one of the most profound reasons magnetars serve as cosmic laboratories. They show us what happens to matter under extreme conditions. Physicists are particularly fascinated by the interiors of these stars, where pressures and densities exceed anything possible in Earth-based experiments. A single teaspoon of neutron star material would weigh about 1 billion tons. Inside, matter is compressed so tightly that protons and electrons merge to form neutrons, creating a quantum fluid unlike anything we encounter in daily life. Magnetars take this already exotic environment and add their colossal magnetic fields, producing states of matter that may not exist anywhere else in the universe. In this sense, magnetars are like natural particle accelerators and pressure chambers, demonstrating forms of matter that push beyond the standard model of physics. But it's not just matter that magnetars stretch, it's also the laws of electromagnetism and relativity. For example, a magnetar's field is so intense that it may give rise to quantum electrodynamic QED effects, predicted by theory but rarely observed. One such phenomenon is vacuum birefringence. Normally, a vacuum is transparent, letting light pass through without interference. But in the presence of a magnetar's extreme field, the vacuum itself begins to act like a prism, bending and polarizing light as if it were a medium. This bizarre effect has been hinted at in observations of magnetars, providing rare evidence of quantum mechanics and relativity colliding in the real universe. General relativity also plays a central role. Magnetars, like all neutron stars, are incredibly compact. A mass greater than our Sun's squeezed into a sphere only about 20 kilometers wide. Their gravity is so intense that space-time itself is curved dramatically around them. Light emitted from their surfaces is bent, delayed, and redshifted by their gravity before it ever reaches our telescopes. This allows astronomers to use magnetars to test Einstein's theory in regimes that are impossible to replicate otherwise. Just as black holes provide one set of extreme conditions for relativity, magnetars provide another, with the added twist of ultra-strong magnetic fields interwoven into their structure. Magnetars also act as natural particle accelerators. Their magnetic reconnection events, when magnetic field lines snap and reconnect, release bursts of energy capable of accelerating particles to near light speeds. These particles, in turn, generate radiation across the electromagnetic spectrum, from radio waves to gamma rays. By studying these emissions, astronomers can test theories of plasma physics, magnetic reconnection, and high-energy radiation processes at levels unattainable in Earth's largest particle colliders. The Sun offers a mild version of this phenomenon through solar flares, but magnetars demonstrate it on a scale that dwarfs anything our star can produce. Another crucial aspect of magnetars as laboratories is their role in illuminating the connection between quantum mechanics and astrophysics. For decades, physicists have sought ways to bridge the gap between the smallest scales of quantum particles and the largest scales of cosmic objects governed by relativity. Magnetars exist right at that intersection. Their interiors are governed by quantum degeneracy pressure. Their magnetism warps the vacuum, and their gravity curves space-time all at once. To study a magnetar is to study the frontier of physics itself, where the most fundamental theories of nature collide and must work together. And then there is the human element. We cannot build machines large or powerful enough to simulate magnetar conditions. Even the Large Hadron Collider, the most powerful accelerator on Earth, pales in comparison to the energies naturally produced in a magnetar's magnetosphere. So nature provides the experiment for us. Each burst, flare, and emission is a data point in a cosmic experiment we could never design ourselves. Magnetars remind us that the universe itself is the greatest laboratory, conducting experiments on scales and with energies that dwarf human ingenuity. These insights ripple outward. By studying magnetars, we gain a better understanding of nuclear physics, quantum mechanics, relativity, plasma physics, and even the origins of high-energy cosmic phenomena like gamma-ray bursts and fast radio bursts. They are like Rosetta Stones for extreme physics, offering us clues to puzzles that remain unsolved in our current models. Their rarity makes them precious, because every observation could provide a breakthrough in understanding forces that shape the cosmos at its deepest level. And yet, despite all we've learned, magnetars continue to defy expectations. Their very existence poses questions about how stars evolve, how magnetic fields are generated and sustained, and whether even more exotic forms of matter, such as quark matter or hyperons, might lurk within their dense cores. They are not just objects of study, they are ongoing mysteries, reminding us how much we still don't know about the fundamental workings of the universe. But as we marvel at what magnetars reveal, another thought naturally arises. If they are so valuable as cosmic laboratories, could humanity ever directly harness the insights they offer? Could understanding magnetars lead to new technologies, or will their lessons forever remain on a scale too vast for us to replicate? For all the incredible progress astronomers have made in uncovering the secrets of magnetars, these rare stars remain shrouded in mystery. In many ways, every discovery about them raises more questions than it answers. They are some of the most exotic objects in the cosmos, yet the science surrounding them is still incomplete. As cosmic laboratories, they show us what physics looks like when pushed to extremes. But as cosmic enigmas, they remind us how much we don't yet understand. Magnetars sit at the boundary between knowledge and speculation, inviting us to ask bold questions about their origins, their evolution, and their influence on the wider universe. One of the biggest unsolved mysteries is why only some stars become magnetars at all. We know that neutron stars are born from supernova explosions, and we know magnetars are an ultra-rare subclass of neutron stars, but the exact branching point is still unclear. Why does one collapsing star end up as a pulsar, while another under seemingly similar conditions becomes a magnetar? Current theories suggest it requires a narrow range of initial conditions, such as a very specific mass, an unusually fast rotation speed, or special internal dynamics during the collapse. But these remain hypotheses. It's possible that subtle differences in a star's core during its final moments decide the outcome, but without a complete model, astronomers can only guess. Each newly discovered magnetar forces us to rethink these assumptions because they don't always fit neatly into the expected categories. Another central puzzle is how magnetars generate their mind-bending magnetic fields in the first place. The leading theory suggests that when a massive star collapses into a neutron star, its core spins extremely rapidly, amplifying its magnetic field through a process similar to a dynamo. In the case of magnetars, this dynamo effect could be supercharged by rapid rotation and turbulent fluid motion, leading to fields billions of times stronger than typical neutron stars. But here's the problem. Models struggle to explain exactly how those fields are sustained, or why they decay so quickly compared to pulsars. If magnetars can build such colossal magnetic energy, what mechanism stops other neutron stars from doing the same? Do magnetars require some unique seed condition in their parent stars, or is there an unknown physical process at work inside them? These are questions without clear answers. Linked to that is the question of field decay and evolution. Magnetars are relatively short-lived in cosmic terms, maintaining their hypermagnetism for about 10,000 years before fading into less extreme neutron stars. But how exactly does that decay happen? Is it a smooth weakening, or does it collapse in sudden jumps triggered by violent starquakes? Observations suggest both possibilities. Some magnetars flare wildly, releasing massive bursts of energy, while others remain eerily quiet for long periods, hinting at a hidden cycle of magnetic stress and release. If we could understand this process, we might gain insights into not only magnetars, but the life cycles of all neutron stars. Another unsolved mystery lies in their connection to cosmic phenomena, like fast radio bursts, FRBS, and gamma-ray bursts, GRBS. Magnetars are prime suspects for the origins of both, but the evidence is still circumstantial. We know that at least one FRB has been linked to a magnetar in our galaxy, but do all FRBS come from magnetars, or just some? Similarly, while magnetars are thought to produce short GRBs, the mechanics of how these explosions occur remain unclear. Are they the result of starquakes, magnetic reconnection events, or do they occur only in magnetars with particularly unstable fields? These are ongoing debates, and every new burst detection adds both clues and contradictions to the picture. Even the internal composition of magnetars is a puzzle. Their immense density suggests they could harbour exotic states of matter, quark matter, hyperons, or strange particles that can't exist under normal conditions. Do magnetars have solid cores, or do they contain fluids of deconfined quarks? Could their extreme conditions reveal aspects of quantum chromodynamics, the theory that governs the strong nuclear force, which are otherwise inaccessible? If so, magnetars could hold the key to understanding some of the deepest mysteries of particle physics. Yet without a way to probe their interiors directly, astronomers must infer answers from subtle observations of their behavior. And then there's the question of why magnetars flare the way they do. Some produce bursts of radiation so powerful they briefly outshine the rest of the galaxy, while others simmer quietly with little outward activity. What distinguishes a quiet magnetar from an explosive one? Is it purely the strength of the magnetic field? Or is it related to the structure of their crust, the buildup of stresses, or hidden rotational properties? Until we can watch one in action up close, we're left piecing together fragments from distant signals. Lastly, there's the larger scale mystery. What role do magnetars play in the universe as a whole? With only around 30 known examples in our galaxy, their rarity makes them seem like mere cosmic curiosities. But on a universal scale, they may be more common, and their bursts of energy could have significant consequences. They might seed elements into space, alter galactic environments with their radiation, or even influence the chemistry of life by sending bursts of gamma rays across interstellar distances. Their role may be subtle, but in a universe of interconnected processes, even rare objects can leave deep imprints. What makes these unsolved mysteries so tantalizing is that every magnetar observed has the potential to rewrite the textbooks. They are not static relics of dead stars, but dynamic, unpredictable, and powerful phenomena. Each flare, quake, or pulse they emit is a message from the edge of physics, daring us to decipher it. Magnetars remind us that the universe is not fully mapped out, that even among the billions of stars we know, there are still classes of objects that refuse to be fully understood. And while astronomers continue to unravel these mysteries, another question naturally follows. Could solving the puzzles of magnetars also solve deeper puzzles about the universe itself? If these stars are laboratories of extreme physics, then perhaps the secrets they hold could unlock answers to questions about the fundamental forces of nature, the behavior of matter at its limits, and even the origins of some of the universe's most violent events. As we bring this journey to a close, it's impossible not to pause and reflect on just how extraordinary magnetars truly are. In a galaxy of hundreds of billions of stars, they are the ultimate outliers, cosmic monsters born from death, wielding powers so immense that human imagination struggles to contain them. Their magnetic fields twist the very fabric of matter. Their quakes release energies that dwarf the sun's output across millennia, and their brief but violent lives serve as both a warning and a revelation. They are the rarest of the rare, the violent children of supernovae, and each one reminds us that the universe is not simply a place of beauty and order, but also of chaos, violence, and extremes beyond comprehension. What makes them even more haunting is their fleeting existence. They flare brightly, burn violently, and then fade into quieter forms, leaving behind only the echoes of their once monstrous power. Their rarity is not only a matter of statistics, it is a reflection of how narrowly tuned the universe must be for them to exist at all. The precise alignment of mass, spin, collapse, and cosmic chance conspires to forge a magnetar, and even then, their lives are measured in mere thousands of years. In cosmic terms, they are like sparks flying from a fire, brief, intense, unforgettable. And yet, in their short lifespans, they shape our understanding of astrophysics in profound ways. They act as windows into realms of physics we could never create on Earth, revealing how matter behaves under unimaginable density, how magnetic fields bend the rules of atomic structure, and how energy can be released in sudden catastrophic bursts. They may even be the key to solving cosmic puzzles like gamma-ray bursts and fast radio bursts, mysteries that ripple across the universe and challenge us to look deeper. Each magnetar is both a laboratory and a riddle, a place where our theories are tested against nature's most unforgiving conditions. When we step back and take the long view, magnetars become more than just astronomical curiosities. They are a reminder of just how small and fragile we are in the face of the cosmos. A single nearby magnetar could strip Earth of its atmosphere, sterilizing our planet in moments. Yet, from the safety of thousands of light years away, we can study them without fear, turning their fury into knowledge. They are monsters, yes, but monsters that teach us, expand us, and force us to confront the boundaries of what we know. Ultimately, the story of Magnetars is the story of the universe itself, violent, mysterious, and profoundly strange. They remind us that the cosmos is not built solely on steady or predictable patterns, but also on rare, chaotic outbursts that defy expectations. And it is often those rare outliers, the ones that don't fit neatly into the mold, that teach us the most. Magnetars are proof that the universe still holds surprises, still hides secrets, and still humbles us with its raw, terrifying power. So the next time you look up at the night sky, think of this. Somewhere out there, hidden among the billions of ordinary stars, a handful of magnetars lurk. Silent most of the time, invisible to the naked eye, yet capable of unleashing more energy in an instant than our sun will produce across its entire lifetime. They are the rarest monsters in the cosmos, and they serve as both a warning of nature's extremes and an invitation to keep searching for the unknown. Because if magnetars can exist, then the universe is surely stranger, wilder, and more terrifying than we have ever dared to dream. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.